All right, good afternoon. As I would have expected based on past classes that I've taught, the third exam, the average does go down. It went down, average was about 67, close to there, which I would say would be typical for this class. So just to let you know, I noticed there were some people who did significantly better than their last test and some people who had some difficulty. And that happens when this material continues to build, and I think I told you on the first day of class that was the case. So I didn't lie to you. You know, there's still 3 more chapters. We'll see if we finish all of them. I'm hoping to get a lot of it done, but the chapter 12, we'll see how we go. We'll just go with what the pace is and see where it goes by the end. The final exam will be half of it roughly comprehensive from the first material from the first 3 exams, and then half of it will be the new material. So there is opportunity, I think, if you did do poorly on this exam, to raise that on the final exam, because it does include all the material. As well as the quizzes. If you've been diligent about being here for quizzes, that might be able to help you out too. So, question? Your exam? Oh, go ahead. So I do want to move on and talk about Chapter 10. And for those of you who are looking at my past class notes and from the previous years, in the previous textbook we used, it's actually not in the 341 class where we talk about these subjects. So Chapters 10, 11, and 12 in this book was chapters, I think 14, 15, and 16 in the old textbook, which was covered in Chem 342. So if you go to my Chem 342 page, which is listed on the front, you can find the old material that's covered that we're going to be talking about for the rest of this class. I like the way this book organizes the material a little better in terms of the progression, because we've been talking a lot about alkene chemistry, alkyne chemistry, electrophilic addition, pi systems, and this really continues that. We're talking about how the chemistry is similar, but there are some distinct changes when we start to have multiple pi systems in a row. It's something which we call conjugation. Conjugation, oh, I actually forgot something. I have to go to my office for just a second. This is a chemistry class, and what chemistry class would be complete without a demonstration? So we'll do a demo in a minute. Talking about conjugation, whenever we have multiple pi bonds that are lined up in a row, we refer to those as conjugated systems. And we're going to talk a lot about carbon-carbon double bond conjugation. But conjugation is also something we refer to when we have pi bonds to other atoms as well. So you can have CO double bonds and CN double bonds connected with other CC double bonds. Those are also conjugated systems. So you can see from these examples, 1,3-butadiene, if you look at the 2 alternating double, single, double bonds, okay, the pi system, or the pi bonds, are made up of p orbitals. So if you look at the 4 carbons in a row, right, there's a p orbital on every carbon. And they can all be aligned in the same direction. So that means that there could be communication of the electrons all throughout. Whereas if you have something like 1,4-pentadiene, you have a carbon in between those 2 double bonds. This is an sp3 hybridized carbon. So what happens is there is no p orbital on that carbon, and so there's no connection or communication between this double bond and that double bond. Okay, and that delocalization of the electrons in the pi system leads to situations where we have increased stability as well as different kinds of reactivity. And in fact, the double bonds, when we have a lot of conjugation, it actually allows the electrons to spread out over a longer range, and they are excited more easily by light. So you use less energetic light to excite the electrons in there. That means compounds with a lot of conjugation are usually highly colored compounds. So for example, beta-carotene. This is a substituent from carrots. It actually leads to making retinol in your eyes so that you can actually see. But it has an orange color because of this large extended conjugation. So it's absorbing a wavelength of light, which allows only orange to pass through it. So it's absorbing other colors of the white light. Here's another one. This is another colored compound called lycopene. It's the red color from tomatoes. And you can see what I've highlighted in red here are the double bonds in that molecule, which are conjugated or right next to each other. So you always see this double bond, single bond, double bond, single bond. Again, there's a p orbital on every carbon in that red section next to another one. And if you take a look at tomato juice, here's a graduated cylinder of tomato juice. And right next to it, you can see the red color, right? This is a solution of bromine water. What do you think would happen if I added bromine water to tomato juice? The picture doesn't show up too well on here, but you see this starts to turn blue-green, right? This is after the bromine water has been added. So what's happening here? You're breaking the pi bonds. How are we breaking the pi bonds? You're brominating, right? We've talked about this reaction. What you're doing is adding Br2, okay? And then as you add more and more Br2, you might see that there's a concentration gradient. Tomato juice is thick enough, so you have different concentrations of Br2. More and more of these double bonds get conjugated, and so we're breaking up that extended pi system into smaller pieces. Okay? And we see that by a color change, because once you start changing the distance or the length of the conjugated system, the wavelength of light it absorbs changes. So you can actually see that quite nicely in this visualization. Which brings me to another demonstration. This is a molecule which is highly colored as well. These are anthocyanins, depending on what the specific substituents are. There's a whole family of these. And they are the red color that's found in lots of fruits, like grapes. This is a diluted cranberry grape juice right here. Okay? Now, you can see the red color. It's usually a dark red, dark purple, the color of wine, many fruits. And you'll see what happens if I take this and add sodium hydroxide. Uh-oh, getting low. There you go. See the color change? Okay, what's happening here? That no longer looks like appetizing grape juice. So, in this molecule, there are some acidic hydrogens, and it even has an oxygen with a formal plus charge in it. And when you add sodium hydroxide, you actually change the structure because it has deprotonated that, and it has deprotonated this one as well, and rearranged this, neutralized that plus charge. And it might be a subtle change, but it has changed the overall conjugated pi systems in this molecule, that it changed the wavelength of light that it absorbs. So one of the aspects of large conjugation is the issue of color. And of course, way back in the 19th century, I think organic chemistry and organic synthesis really started to come about because of German chemists trying to make dyes, so trying to make colors. So that's kind of a side light here. When we talk about the chemistry of conjugated systems, we need to think about a double bond and how it interacts with other reactive functionality that we've talked about. So we have seen in this class already examples of carbocations, okay, and we've seen examples of free radicals, and we've seen examples of carbanions. And when we have carbons that have too few electrons or too more electrons and not bonded, and it's next to another pi double bond, that really is a system which is conjugated as well. It doesn't just have to be more stable diene systems. It can be a reactive, either a whole, an empty orbital, one electron, or two electrons in the orbital. Okay, this 3-carbon unit, by the way, we refer to as an allyl group. So this is an allylic carbocation, an allylic free radical, or an allylic carbanion. If you think about the way I've drawn this here with these pi bonds, and notice I drew the carbocation also in a p orbital, right? What happens actually is that the 2 electrons that are here and the empty plus charge, actually that's spread out over the whole molecule. We could draw resonance forms for this. If you shift those 2 electrons over here, you can draw a resonance form for that carbocation and put the plus charge on the other carbon, move the double bond over. What exists, again, is something spread out in between those 2 resonance forms. And the same thing, exactly the same thing we could do with the free radical. We just take 1 electron over here to form a double bond, push the other electron up. You can draw a resonance form which looks like that. Okay, and negative charge as well. Push those electrons down there to form a bond and push those up on the carbon. Then you have this resonance form for the allylic carbanion. And I've showed an example here with 1 double bond next to a plus charge, this so-called allyl group. But if you have further conjugation, you could spread that plus charge out all the way down. Or if you have a negative charge, you could spread that negative charge out all the way down. Okay? What do you think then would be the relative stability of, say, this allyl carbocation versus a propyl carbocation? What would you expect to be more stable?
The allyl carbocation.
The allyl carbocation would be more stable. Remember, whenever we can spread out charge or spread out electrons, the lower energy it is, the more stable it becomes. And so that's absolutely right. In all of these cases, whether it's a negative charge, a free radical, or a carbocation, the more we can spread it out or delocalize that charge or electrons, the more stable it is. Okay? Even if it's not reactive species like this. So I do want to point out some of the terminology we use. I mentioned those were allylic carbocations, allylic free radicals, and this is a general term we use whenever we have a double bond and a CH2 or an sp3 carbon and a functional group. So an allylic alcohol or an allylic bromide, for an example. And the hydrogens on those carbons. We have specific terminology to refer to hydrogens on an sp2 double bonded carbon or an sp3 carbon which is adjacent to a pi bond. So we have vinylic hydrogens. Those are the ones that are on the sp2 hybridized carbons. And the hydrogens which are adjacent are allylic hydrogens. Okay, and that's important because the double bond changes the strength and the nature and the reactivity of those groups. The allylic bromide has a slightly different reactivity than propyl bromide. Okay, and we'll see that in a little bit. We talked about in the last chapter on alkynes how the acidity of the CH bond changes depending on the hybridization, right? So even these vinylic hydrogens have a different reactivity than just an alkane. It's a little more acidic than an alkane. But these allylic hydrogens are even more weakened, this bond. These hydrogens are accessible because if you break this bond and make things with it, you make a carbocation, well not with a hydrogen, but most likely a free radical that free radical next to a double bond is going to be more stable than a free radical not next to a double bond. So it's easier to take those hydrogens off. Well, let's look a little more closely at the allylic carbocation. So remember we had this allylic carbocation, and I can draw a resonance structure for that. Okay, if I push those electrons over here, that moves the double bond between the right two carbons, leaving the empty orbital there. And so one thing you notice looking at those two different resonance forms for the allyl carbocation, right? Where is the plus charge located among those three carbons? It's located on the two ends. Okay? The plus charge, there's a plus charge on that end carbon on the right, and there's plus character on the end carbon on the left. None of these resonance forms put the empty orbital, the plus charge, on the middle carbon. Okay? And that's reflected when you think about what that structure really looks like, some hybrid of those resonance forms in between. It looks something like this, okay? Where the pi orbitals or the pi system is spread out among all three carbons, but that's 2 electrons and 1 empty, okay, that we're talking about. 2 electrons spread out over 3 carbons, but most of that electron density still is somewhere in the middle, as shown by this electrostatic map, this plot, where we have the 2 end carbons and we have a lot more red color on the middle carbon. That means that there's more plus charge on these ends, as you would expect looking at those resonance forms, and more electron density in the middle. So when you think about reactions and reactivity, you need to know where the charge is. Where are electrons? Where are plus charges? What is electrophile? What is nucleophile? That will dictate to you where things will be reacting and where they won't. Come on. There we go. So one of the things that we have to consider also is that once we have allyl carbocation system, which is unsymmetric, okay, there might also be a little difference in the electron density. And that's what's shown on this electrostatic map. So the allyl carbocation, by the way, we could probably draw this. Sometimes it's drawn with like a dashed line and a plus. And this one actually has a CH3 out here on the end. Okay, there's a CH3 group. Now the plus charge, as shown by these two resonance forms, exists on those 2 carbons. Okay, so you see 2 plus charges. But now, since it's no longer symmetric, one of those resonance forms should be more stable than the other, right? Lower in energy. More substituted carbocations are lower in energy. So if you could, if you had this as an isolated individual molecule, it's not, it just represents an extreme. But you would expect that to be a little bit lower in energy than this one. Okay, so the hybrid, or what actually exists in between there, you would expect there would be more plus charge on this carbon than on this carbon. Okay. And in fact, if you look at the electrostatic potential map, here's the CH3 group. Okay, there's the middle carbon of the 3-carbon allyl. There's the 3-carbon allyl. Okay, and you see more blue over here and less blue on the end. That's reflecting the fact that there's more plus charge probably located on that carbon because it's better able to accommodate the plus charge there. Okay, so if you were to think about reactivity, where would reactivity want to happen fastest? Well, the one that's probably has more plus charge. More plus charge density here, less plus charge density here. Certainly no plus charge density on those carbons. Okay. this shows you some aspects of how having a double bond adjacent to a functional group affects the reactivity, okay, and how it affects the formation of intermediates, and so on. Because if you take a look at the SN1 substitution reaction, we know that tertiary halides react the fastest for SN1 because generating a tertiary carbocation is easier than generating a primary or secondary carbocation. So the first step in an SN1 substitution is loss of the Cl-, right? If you compare these two molecules, they're both tertiary halides, but this one is tertiary and allylic. And that double bond helps to stabilize even more. And so if you form the double bond adjacent to the plus charge, it's still a tertiary carbocation, but now the plus charge is spread out through resonance. Okay, so that's an even better substrate for SN1 if it has that double bond present than just a simple tertiary chloride. Okay, so it shows you the reactivity, and if you look at this, the relative rate's 123 times more adding that double bond than without it. Okay, well, here's another aspect to this. One thing you need to consider, especially when you have an unsymmetric allylic system, okay, this shows you some of the issues involved in this. So we have a chlorine, we have essentially two molecules which would generate the same intermediate, right? The same allyl carbocation if it were to ionize. And in fact, here, since it's, we would think a primary chloride doesn't form a carbocation very easily. Well, it can if it's allylic, and a pretty stable allylic, because if you think about forming that carbocation, loss of the chlorine, right? And I'll just draw it like this first. Okay, that would be the carbocation generated if we lose the chlorine. And from this one, if we lose the chlorine, we generate this nice stable tertiary carbocation. But these aren't different, right? These don't exist. What exists is something in between. These are resonance structures. So in fact, starting from the left chloride or the right chloride, you're generating the exact same intermediate. Something which might be better to draw with some kind of dashed line with a plus charge spread out. Okay. Now, there's probably a little more plus charge on this structure on the left. As we just talked about, if you were to look at the electron density map, you'd see that there'd be more plus charge on the carbon resonance form that would be more substituted, right? And that's reflected in the product. You form this carbocation, the water will add to the carbon that has the most plus charge, preferentially. And so what we see is we see 85% of the reaction mixture giving the alcohol on that carbon, and only 15% of the reaction mixture giving the alcohol on the end. So it doesn't mean the end is unreactive, right? It certainly is. There's certainly plus charge on the end carbon. It's just that there's a greater plus charge on this carbon. So it reacts like that. And it doesn't matter which one you start with, you get the exact same ratio, mixture of the product, because both of them form the same intermediate. Okay, does that make sense? Thinking about how all of this is related to each other. Keep in mind, where is charge and how does it react? Well, not just SN1 reactions are affected by the presence of a double bond. Even, sorry, I have a typo there. That should be SN2 reactions. Even an SN2 substitution reaction shows differences in the rate of the reaction depending on whether you have a double bond conjugated or potentially, say, allylic to your leaving group or not. So here is chloropropane, and if you take the allyl chloride, it reacts 80 times faster for an SN2 substitution. If you use the same nucleophile for both, like, I don't know, CH3S minus, like we had on the test, right? They react 80 times faster. All right? It's not forming the carbocation intermediate. It's not that the carbocation intermediate is less stable or more stable. It's a one-step reaction. But the presence of this double bond does weaken the carbon-chlorine bond also. It makes it more reactive. Okay? So even for SN2 substitution, being allylic is good. This is a really excellent electrophile, by the way, for doing nucleophilic substitution on. Okay, what about allyl radicals? We've talked about free radical chemistry in the context of free radical halogenation of alkanes, and I'm going to go back and talk about that a little bit in this case. But if you consider an allyl radical, okay, an allyl radical or a lone electron also is an unstable species. It's a reactive species, but if you can spread that out, what you see is that, or delocalize it, it provides stability. And so we can draw, again, the resonance form for that allyl radical. All right? So what we really have is radical character on both ends of that allylic system as well. Just like we talked about the carbocation, there's plus charge on both ends. Well, here, we can have radical be reactive on both sides. And if you, this is not an electrostatic map. This is something a little different. This is what we refer to as a spin density map. It's a calculated picture of where electron spin resides. Because remember, electrons have a spin quantum number, right? So they have a spin associated with them. And when you pair up electrons in an orbital, their spins have to be opposite. And so overall, there's a net zero spin. What we see is in molecules with unpaired electrons, we see non-zero spins. And if you calculate it, the computation, the quantum mechanics tells us that there's about a half a spin spread out on the two end carbons. Okay? What that means is that there's radical character, or unpaired electron character, at both ends. Again, spreading out stabilizes. It's lower in energy than if that radical were stuck just on one carbon. And when we think about reactions now that involve radicals, we need to consider that that radical could exist in multiple places. And how it affects reactivity as well. So if we look at the enthalpies of CH bond cleavage, right? This is the energy, the CH bond energy, essentially, the bond dissociation energy. Generally, an alkane, like a primary CH bond on propane, has a delta H of about 101 kilocalories per mole. Okay? Relatively strong bond. Okay? 101 kilocalories per mole is a good, strong bond. An allylic hydrogen, on the other hand, only takes 88 kilocalories per mole to break. What can you say about the bond strength? It's weaker, right? Allylic CH bonds are weaker than alkane CH bonds, normal alkane CH bonds. Even though it's an sp3 hybridized carbon, the fact that you're generating a more stable free radical is what's important for that CH bond strength. Okay, that has effects in chemistry. So do you remember we talked about free radical bromination or free radical chlorination of alkanes? And we saw that if we had methane, we could make chloromethane. If we had butane, we see a mixture of 1 chlorobutane and 2 chlorobutane, right? And we saw more of the 2 chlorobutane. Why did we see more of the 2 chlorobutane? It's more substituted. The secondary hydrogen on a secondary carbon is easier to break to form a free radical than the hydrogen on a primary carbon. Why? A secondary free radical is more stable than a primary free radical. And even though there were 6 primaries on butane and 4 secondaries, statistically, we still got more of the product from the secondary bond cleavage because it's easier to break. Reactions happen faster if the bonds are weaker, right? That's the case here. If this is easier to break and weaker and lower energy to generate that radical, it's going to be much, much easier to do free radical halogenation in these positions which are allylic. So if you see these examples, right, free radical halogenation, this reaction works really well, allyl chloride. It doesn't react on the double bond if we're doing chlorine radicals, okay? This is not Cl+. This is Cl radicals activated by heat or light. Well, allyl chloride, just propene, you can see you get the allyl chloride as the product. But if you look at this structure, cyclopentene, okay, there are 3 different kinds of hydrogens on here. Okay? What 3 kinds of hydrogens are present on cyclopentene? Let's look at all these hydrogens. There are hydrogens attached to the double bond carbons. We call those what? Vinylic hydrogens. Vinylic. Okay? There are hydrogens attached to the allylic position. Oops, that's on the carbon. By the way, both sides, this is also allylic relative to the double bond. Okay? And finally, there are just normal alkane. Let's see, what color should I use? Green. There are just normal alkane sp3 hybridized CHs. Each of those CHs are different. These are the weakest bonds in this molecule, the ones I've highlighted in blue, because you generate the most stable free radical if you were to break it and pull it off. And so if you do a free radical halogenation, what we see is replacement of the allylic hydrogen with a bromine. So you get very selective, this is the exclusive product if you do this carefully, substitution of a hydrogen under free radical conditions in the allylic position. By the way, I don't know why your book didn't talk about this reagent earlier, but they introduced it in this chapter, something we called NBS, or N-bromosuccinimide. This is a very practical and useful form for bromine radicals, because this N-bromine bond is easy to break into radicals. Just by a little bit of heat or light, you'll generate bromine radicals. And we know that's the start to everything, right? Once you generate those free radicals, then you have the free radical chain mechanism. So if I asked you right now to write the free radical chain mechanism for this, would you be able to do that? Yes? Of course you can. Of course you can. Let's see, I should do that. I have a blank slide. Let's do that. Okay, what's the initiation step? Initiation? NBS, or you can use Br2 or Cl2, but this is a nice one. Initiation step? Heat or light, a photon of light is enough to break this apart. I'm not going to worry too much about this. Instead of 2 bromine radicals, we break them apart into these 2 radicals. Okay? This part eventually grabs a hydrogen from somewhere and becomes a stable succinimide, is the name of it. But the bromine radical is what does the job. Okay? We know that bromine radical, or I guess this radical, either one, can react with our molecule And I'll just show one of the allylic hydrogens. That's the easiest one to break. So whatever radical we have, whether it's bromine dot or this N dot, I'll just say Y radical, whatever it is. We'll grab that hydrogen and generate now our free radical. Plus either HBr or NH. Okay? So that's easy to do in that position. And again, there are two resonance forms. This happens to be symmetric, so it doesn't really matter. We can draw this resonance form as well. That, in the next step, I'll just do it from here. We'll react with NBS, again, to grab the bromine, to grab the product, plus that, probably that succinimide radical. Anyway, we generate a free radical that can go on again to grab another hydrogen, and so on. And so this is actually a good source for Br, but the exact same mechanism. The only difference now is our substrate, our CH activation that we're talking about is made very selective and possible because of the presence of this double bond. That allylic hydrogen is important. Okay. By the way, there's another term which you'll probably learn in some of the later chapters as well that's related to this. Sorry, did I just erase that for everybody? I'm a little too quick sometimes. If you have a benzene ring, okay, a benzene, let's just take something like this. Benzene also has different kinds of hydrogens. The pi system of the benzene helps to stabilize charges, plus charge, minus charge, free radicals, just like a single double bond does. And so these positions adjacent to a benzene ring react very similarly. We call these benzylic positions. Benzylic. Okay, as opposed to allylic. That's allyl. That's benzyl. And you can do very selective bromination on these also. If you carry out the same reaction with NBS and light, you get formation exclusively of bromination next to the benzene ring on the alkane carbon in the benzylic position. Okay, for the exact same reason. That's the weakest CH bond because you generate the most stable free radical intermediate. Okay? Everybody with me? Well, allocarbanions we can also think about in terms of their stability as well. It's very similar to one of the systems we've seen before, right? So if you think about the resonance structure, you can delocalize the minus charge. Now we've just switched from plus or free radical to minus. That looks very similar to our acetate ion, right? It's just instead of oxygens on the end, we have carbons on the end. So an allylic delocalization is exactly the same. It's just that it's not oxygen, it's all carbon. And the electrostatic potential map, although it doesn't show this very red, it certainly shows there's no red in the middle, right? Because the negative charge now is spread out on the two ends. And if you think about this as a nucleophile, for example, as opposed to an electrophile, that's where reactivity will occur in a negative sense. Okay, again, what exists is something in between. That's reflected in the pKa as well. So remember we talked about the ability to deprotonate an alkane. Obviously the pKa is way too high to do that. You could not do that. If you went to vinylic hydrogens or an acetylene hydrogen, alkyne hydrogen, like from the last chapter, pKa goes down enough that we could deprotonate it. But even an allylic, now this is just sp3 CH bond. If you had a strong enough base, you could deprotonate it. The pK is about 43. Still very high, but it's certainly easier to do that than an isolated alkane because the negative charge is now delocalized. So even with carbanions, that delocalization in an allylic system helps to stabilize. Well, let's talk a little bit more about the conjugation now of not really the reactive systems, but the more stable systems, the double bonds. So we don't have plus charge, we don't have reactive sites necessarily of free radicals or negative charges, but just the dienes. And if you look at the two isomers of pentadiene, right? We saw that 1,4-pentadiene has this CH2 group in the middle. Okay, that prevents, here in the middle, that prevents any delocalization of electrons all throughout. So we just have two isolated double bonds. And the reactivity of pentadiene reacts as all the chemistry we've talked about in terms of reactions of isolated double bonds. Okay, if you have 1,3-pentadiene on the other hand, notice in this molecular orbital map showing the pi system that the 4 electrons in the system are spread out across all 4 carbons. There's no break in between. And again, that's because there's a p orbital on every carbon. All right, so that's conjugated. This is not conjugated. And that has impacts on the reactivity of dienes also. Okay, what about this? This is a functional group which we call an alene. It's essentially a 1,2 diene. So we saw 1,4-pentadiene, we saw 1,3-pentadiene. There was one single bond in between the 2 pi bonds, but that allows all the p orbitals on all 4 carbons. Well, here's a system where we have 2 double bonds that are on right next to each other, what we call an alene or accumulated diene. What do you think the reactivity and structure of this is going to be? Let's talk about the structure. What is the structure? What is the hybridization of the carbons? sp2, not all of them.
Isn't the middle one sp?
That's exactly right. Notice this middle carbon. This middle carbon has 2 pi bonds on it. Okay? Where else have we seen 2 pi bonds to a carbon? Alkyne, right? An alene or accumulated diene, where the 2 double bonds are going off from the same carbon, they're just going to different carbons, not to the same carbon. Like in alkyne, both pi bonds are between the same carbons. Here we have 2 pi bonds, but going in opposite directions. But they can't exist in the same plane. All right, and that's important to recognize. In order for this to be able to bond, here's the structure. So we have 1 pi bond here that I've shown in red that has to be 90 degrees or orthogonal to the pi bond to the other carbon. Okay? So the result is, notice this middle carbon, 180 degree bond angle, 2 pi bonds on it, 2p orbitals. So this has to be sp hybridized, whereas the 2 n carbons are sp2 hybridized. It's very important to recognize that because this is very different than a conjugated diene system. In a conjugated diene system, where you have a single bond in between and 2 double bonds, the pi system is all connected in one plane. Okay? Here they have to be orthogonal, otherwise you can't have this structure. As a side note, I should mention, notice the structure that I've drawn over here. Okay? Because of the orientation of the 2 pi bonds, if this red p orbital is in the plane of the board, going up and down, that means we have a hydrogen that's coming out towards us and a hydrogen going back away from us. Okay? So that's coming out and going back onto the board. But if you look at that blue pi bond, if that p orbital of the pi bond is pointing towards us and away from us, that means the two CH bonds are in the plane of the board. Okay? What does that kind of look like? Let me just draw a tetrahedral methane. Okay, that's methane. Methane is sp3, right? It's a tetrahedral. We learned in chapter 7 that tetrahedral carbons, if you have 4 different groups attached, then it's different than this mirror image, right? So we have stereochemistry of enantiomers. This is a very interesting molecule, allenes, because it's kind of like a tetrahedral carbon, but extended out with another carbon in between, right? That's what an allene structure is sort of like. So let's say you have different groups on the allene, on the ends. It could be chiral. There's actually some stereochemical aspects to these allene structures. With just hydrogens, it's not chiral. Its mirror image is the same. But if you have something different on this end, let's say we have CH3 here on the top, hydrogen on the bottom, and CH3 here coming towards us and hydrogen going back. There's no stereogenic center. There's no one carbon with 4 different groups attached. But even that is chiral. Its mirror image is not the same. It's another example of helicochirality. So if you look from the side, you have a CH3 up, and you go to the left as you go to the back carbon. It's sort of twisting to the left in the helix. If you switch those two in the back, then you would twist to the right. And actually, that's a mirror image. So there's some interesting chiral aspects to this as well. But I want you to recognize the structure and the hybridization of these carbons, because that middle carbon is an sp hybridized, not sp2, because it has 2 pi bonds to it. 2 pi bonds, 2 sigma bonds, it has to be hybridized. Okay, well, let's talk a little bit about how conjugation affects stability. We know very well that an alkene that's more substituted or less substituted affects its energy, right, its stability. So 1 pentene, if you do hydrogenation, takes 126 kilojoules per mole, whereas 2 pentene, where it's more substituted, takes less energy to hydrogenate. It's lower in energy to start with, okay, or releases less energy. Look at the non-conjugated pentadiene and the conjugated pentadiene. The non-conjugated pentadiene releases 126 plus 126, essentially double the 1 double bond here. Whereas if it's conjugated, it's not releasing 126 kilojoules per mole more. It's only releasing 111 kilojoules per mole more. So it's more stable than what you would predict if they were just 2 isolated double bonds. Okay, and that extra stability is coming from the fact that the pi system is delocalized in conjugation. And so we can measure that directly by doing this heat of hydrogenation comparison. And the cumulines are the allene. Since they are orthogonal, you don't get that benefit, and actually it's higher in energy than just a doubling of 1 double bond. So if you look at propene, hydrogenation, it releases about 30 kilocalories, sorry, I switched units, kilocalories per mole. If you take the allene, it actually releases, it's higher in energy than just 2 isolated double bonds. So that actually is a higher energy state, this allene. They tend to be pretty reactive species. So, that's another important aspect to differentiate that really from conjugated systems. Okay, I think I'm going to stop there today. I want to talk a lot more about conjugation and how it affects conformation. And we're going to talk about reactions of double bonds on Friday.